welcome to a new programming video here. In this video, we're going to go over a little bit about a linked list. So a linked list is another implementation of the list interface, which uses a data structure known as a node. Now, in this case, what we're going to do is we're going to be using nodes that have a reference to the next node in the chain and a little bit of data. In most applications, we'll be using nodes that contain a reference not only to the next node in the chain, but also the previous node in the chain. An implementation of a list with that kind of data structure happens to be called a doubly linked list, but in this case, we're going to be using this implementation right here, which would make the linked list called a singly linked list. So, what we're going to do here is we're going to first start up our chain. We're going to start making a linked list here. We're going to put 9 nodes in it. So as you guys can see, well, we have a little bit of overlap here, so we might change it to 5. Okay, so as you guys can see over here, we've got this chain of linked lists. And in our linked list class, we have this data field known as front, which points to the very start of our chain. So in this case, if our front was not pointing to any bit of data that this whole chain here had, we wouldn't have a reference to this entire list over here, and basically the job of a garbage collector, we'd collect this data and remove it forever. So let's keep that in mind as far as things go. Let's actually take a look at our list. So the first thing we do is we have this method called add to front. And so what add to front does is it creates this new node, and it basically says if the front is pointing to nothing, which in this case it is, we're going to add our new node right over here. If it's not, in this case, what we're going to do is we're going to have our front point to this new node over here. But before we actually do that, we need to keep a reference to the rest of the nodes in this chain that we've created. Otherwise, as I stated before, if we just move our front pointer to be over this new node, we wouldn't have any reference to this chain, and we'd actually lose it forever. And that's not good as far as things go. So what we want to do is when we create this new node, we want to have we want to set its next field to be pointing to what the front is originally pointing to, which is this bit of data over here. So once we actually create that chain over here, what we can do is we can then move the front pointer, this pointer over here, this little arrow, to be pointing to this new node. And I'm going to do a little bit of freehand drawing to try to get rid of that chain right there. So we get rid of this point and we move it down here after we've already set this point over here, so that we can maintain the structure of our list. So I'm going to get rid of that jargon. So that's what add and add to front are doing. Remember, add to front is nothing more than a specialized version of our add method. Our add method is basically finding out what index we'd like to insert a new node into. So for example, if I wanted to add a node at index 2, which would be over here, what I want to do is I want to say this node is now pointing to this node over here, and this new node is now pointing to the next node in the chain, which would happen to be this node right here. But once again, follows the same principle of when we found out the place we want to add the node, or one spot before it, what we want to do is we want to create that new node and set its next value to be equal to the next item from the previous, so that we can then move the previous node's pointer to be pointing to this new node that we've constructed. So that's all that's doing over here. The next thing we're going to deal with is a method called remove. So I'm going to actually draw or you know what, I'm going to actually delete this. We actually don't need this. We're going to add a new costume over here to this sprite. It's just going to be a sort of just black block over here. We're going to shrink it a little bit. This is going to represent the node that we remove. So in this case, if we wanted to remove a node at index 2, we would traverse through our list until we find index 1, and then we'd say we set index 1's new pointer to point not at this node, but the node after it. So what that's essentially doing is blocking off this node as a whole. This node no longer exists because we've lost it in the chain, and the garbage collector picks it up on its way out the door. So that's what that's doing there. We do have a couple of special conditions. What happens if we're dealing with the front? If the front happens to be the thing we want to remove, then all we do is set front to be equal to the next thing in the chain. And once again, what we want to do is when we successfully remove, we decrement the size. When we unsuccessfully remove, we don't want to decrement the size, but we want to return false because our remove method is returning basically an indication as to whether or not we were successful in our removal or if we failed. The get, all that's doing is let me hide this really quickly. All that's doing is it's saying give me an index or not, was it give me an index? Yeah, give me an index, and I'm going to try to see if I can find that node. Now, if you give me an index that happens to be outside of the boundaries of my size, then I'm just going to return null to you, which is what's going on over here. If you give me a number that happens to be within the boundaries, then I'm going to try to find that node. Remember, when I say in the boundaries, I mean zero-based indexing here. So, for example, if I wanted to find a node at index 5, I would traverse through this list. So I'd go 0, 1, 2, 3, 4, 5. In this case, it's null, and that's not good as far as things go. If they give me 6, I already know that that should be null, so I don't want to have to traverse and check that. That's why I have the special case right over here. Now, if it happens to be in the list, like let's say we want to get index 4, or get the node at index 4, we traverse from 0, 1, 2, 3, and 4, and return this node over here. So we could return the node itself, but in this case what I decided to do was return a toString method, which basically represents the node as a JSON object down here. So now that we've gotten that, get size is pretty self-intuitive. Since we're keeping track of the size of our list constantly, we can just return that data from a data field. The next thing is our toString method. As with most cases, when we deal with multiple objects that we're going to be traversing through, we tend to want to use a thing called a string builder so that we don't constantly construct new strings over and over and over again. That takes up way too much time and way too much memory. So fortunately we have the string builder, which basically just creates a list of characters. And then what we do is we call its toString method. So depending on this toString method, it could take a total of 2n in terms of the runtime, where n is the number of nodes we traverse. This only takes n, which is good. This might only take n in the worst case, so that's why we get the 2n. Now we're going to deal with, let's talk about the node a little bit. We've already kind of shown a little bit of what the node looks like. Over here, when we look at its costume, it has a data field and a next field, which points to the next node in the chain, which is what we have over here. Here's our basic constructor, which calls the overloaded constructor and sets the appropriate data. Then we have the get methods and then the set method. So, sorry about that. Let's actually take a look at this program in action. So we're going to compile the list driver here that we wrote in the last video, and we're going to run it. So we're dealing with LinkedList this time. We're going to add a 6 to our list, and we're just going to give it jargon, and it's going to automatically append it to the very end of our list. And since there were no elements in our list, it just kind of inserted it over here. Now what I'm going to do is I'm going to remove that item, and it says we successfully removed the item. So, oops, a little bit of scanner mix-up there. Next thing we're going to do is we're going to add 6 back into the item, or back into our list, but we're going to add it at index 0 and see what happens. So that appears to work. We're going to add a few more numbers, feed it some jargon. Okay, now that we've got a few numbers here, I want to add it in between the 6 and the 5, so that's going to be an index 1, according to my chains. So I'm going to add the number, let's see, let's add the number 9 at index 1. And as you guys can see, it just plopped the 9 in between the two indices over here. Now what we're going to do is we're going to get an item at index 6 and see what happens. So it says the item's null, which is what we expected. Let's try get a get at index 4. Okay, so index 4 is null, so that's good. Let's try to get an item at index 3. So we're going to say get index 3, and as you guys can see, oh, that's a little weird. That's a little funny. It gave us the proper value over here, but then it also gave us this index over here. So our get method, our get method's a little off here. So the get method is just a tad bit off. We could fix this because it's an off by 1 error here. Let's see, 0. We want to run index number of times. So we do index. Okay, now let's try this one more time. Okay, Java, list driver, compile it, let's run it. Alright, we're going to deal with linked lists. We're going to add 6. Oops, we're going to add a 6, position 0. We're going to add a 5 at position 0. We're going to add a 3 at position 1. We're going to add a 7 at the very end of our list. Okay, let's try this one more time. Let's get index. The last item that we want to get is the 7, which happens to be at index 3. So, there we go. Yeah, there we go. Now we got the appropriate representation, which shows the data and then a reference to next. If we wanted to make this look a little more fancy, we could use new lines down here, but we'll leave that for next time. Okay, so let's actually check that we can remove the 6 from our list. Let's remove the 7. Okay, now let's get the size, see if the size is right. Alright, we're going to add a 6 to index 3. Doesn't add it because it's not possible, we don't have an index 3. So let's try adding 6 to index 1. Okay, now let's add a 9 to the very end. Check the size, make sure it works. Okay, so that's pretty good as far as things go. The next thing we should do here is let's actually quickly write a clear method. So, what I'm going to do is, of course, start off with header. Clears the list. It's a void method. It actually doesn't do much of anything other than just reset the front pointer. Remember, what we did before is if we just make it so that front point's null, we lose track of the rest of our list. So it's going to be public void clear. So setting front to null isn't going to be good enough because we also need to set the size to 0 because we're keeping size over here. If we keep size the same amount, our list will kind of get off track and it'll be all weird and wonky. So, so that's how the clear method would work. Of course, what we want to do is we want to add an option for allowing the user to enter clear over here, and then we could do that thing accordingly. So anyways, I hope you guys found this video somewhat informative and useful, and feel free to message me later down the road if you feel the need to do so. But otherwise, have a great day, guys, and I hope this video helped you.